tonight. I want to appreciate you for being around. So, let me share my screen. Oni, let me let me share my screen. Okay. Okay. You have seen my screen, right? So open up the two files.
I'm still trying to open it open.
Let's open up the two files.
If you
We,
had sent it to the mail,
you see,
you need to open transfer to system. So
I transfer it to the system. Can you can you can you do that?
that's sometimes. Um, hold on, no.
No, sure, I will because I want us to follow up. So
Okay, almost there.
all right. So while we are trying to open up our files, a quick reminder: we are on leader-based docking, and leader-based docking involves the use of structure activity relationship of some known compound. We use the activity of some known compounds of similar structure to predict the activity of another compound with unknown activity. So that is what we mean by the leader base. We use the activity of some known structure, some similar structure. We use the activity to predict the activity of an unknown structure, an unknown compound that still has similar structure. So we work on anthraquinone. We want to predict the biological activity of our new anthraquinone drug or our new anthraquinone compound. So we have to look for the biological activity of some already investigated anthraquinone compounds. It must be of same of similarity. Yes, those compounds must be of
Same
similarity.
structure.
Yeah, substructures. So if not, you are doing nonsense. If not, you are doing nonsense. So we and then they must be of same targets. You must target the same receptor, like the same disease target. So if you are working on malaria, maybe you want to work on pyridine derivatives for malaria, you must look for pyridine compounds that have been tested on malaria. I showed you how to do that. Just type pyridine malaria and your pop came, then go for tested compounds under bioassay. So when you do that, you will now get some pyridines that have been worked on. Luckily, you may not see because these are work that has been done. So if no work has been done, you have to change your objectives. So when you get them, we are just working on few. We don't work on few compounds. At least we work on 100 training data. Your training data set should be up to like 100, but here our training data is just 19, just for practice. So when you get them, you get the biological activity, usually in IC50. So when you get the biological activity, then you look out for their chemical descriptors. So I shared two files with you. The training data file contains the training set with their biological activity.
It's in your, there's no ID. It's just my code.
It's just what?
You did not add PubChem ID. You just did only
Yes.
Chemafia.
Smile code and
Okay.
activity. Yeah. Then the other file I shared is on the admet properties, which from these admet properties we can get the chemical descriptors. Now the reason is because these chemical descriptors, they describe the chemical structure. So they are the properties, they are the structural properties. So we are looking at the relationship between the structural properties of this anthraquinone with their biological activity. So if we can build a model that can relate the structural properties with their biological activity, because whatever a compound can do is as a result of the structural properties. So if we can build a model that will relate the structural properties of these known anthraquinones with their biological activity, from that model we can now predict the activity of our training data, of our test data, that is the new anthraquinone we want to investigate without going to the lab. So we can now build a model that we can relate it can predict the activity of our test data, which are the new anthraquinones now. It will then help us predict the activity based on their own chemical descriptors. So what we'll do now is we are going to now select. Last week I wanted to use multiple linear regression. I later decided to use RSM, response surface methodology. Now I noticed that the RSM, some of us is too complex. yeah,
Wow.
it's too complex, and
Which one comes first? One.
yeah, we will use the multiple linear regression, the MLL, right now. Now, the reason why we shall be using the MLR, the multiple linear regression, is because the multiple linear regression works better when the properties has direct effects on the activity. So I want us to know when to use RSM and when to use MLR. Now MLR is used when the properties we are investigating has direct effects on the when the variables has direct effects on the outcome, which is the output. Now, but when then again, I'm giving you two conditions on when to use MLR. One is when the variables we are considering has direct effects on the output, such that variation is not considered. Now, number two, when the variables are constants, like the variables are not expected to change. So, like when we are looking at a structure now, the structural properties of any compound remains the same. They don't change. The number of hydrogen bond remains the same. The number of hydrogen bond acceptors remains the same. The TPSA remains the same. The molar weight remains the same. The solubility remains the same. And all these have direct effects on the activity, and they do not change. They remain constant. So these two conditions meet this our training data set. So that's why I'm going to opt for MLR. MLR. But that of RSM is for mostly for process optimization. Like take for instance, we are doing a reaction, and that reaction is being affected by some conditions. The reaction is being affected by some condition. Let's say extraction yield. Extraction yield. Now, extraction yield might be your output, and then this extraction yield can be affected by some factors like temperature, pressure, the amount, the quantity of the sample. Now, you see that these factors can change, and change in these factors leads to change in the extraction yield. So we if we want to predict that kind of yield, maybe you want to ask yourself, what yield will I expect if I extract 50 gram of my sample at 70 degrees Celsius with a reduced pressure? Or what yield will I expect if I change my gram, the sample to like 10 gram at 100 degrees Celsius with 250 millimeter mercury as pressure? Now you see that because I want to see the variations of my conditions and how they now affect the output, the best method to be used in such optimization is RSM. Then you may even consider, okay, if I increase the mass and leave others constant, what is the effect? And that is why in RSM we have three major conditions. We have the linear conditions, we have the quadratic conditions, and the combination conditions. So I'm trying to put it right now that for linear-based structure design, I will advise you to go with multiple linear regression. So quickly, we are going to look at the equation of multiple linear regression. Please, if you have a question.
Oga Henry, so what you are trying to say is that what we did last week, on Monday, we just wasted our time. Yeah.
No, no,
Oye, na Jeko.
not actually a waste of time, but
Oh,
it's part of the training and the practice.
oh, Jesus.
Why I had to further is the kind of result I was getting. I was not supposed to get those results.
I told you that it was very large. I told you the results that I got.
Yeah, yeah, too
Thousand.
negative.
In fact, no, it's not even that negative. Like the one that I did the second time now, it
Yeah,
was very large, like 8,000 something.
yeah, yeah.
Of
So
which you said activity should be very low.
yeah, yeah. So
Okay.
these are the reasons why I had to go back, because these things are not really done much. Publications on them are not much. So these are self-developed principles out of practice and exposure. So we had to go back and look at it. So we shall be using MLL. So quickly, let me see equation of multiple of MLL. Now, the equation now depends on how many variables we are using, but in this case now, you can use as much variable as possible, right? You can use as much variable as possible. So you can use as much variables as possible. This is the equation. So we can copy it out. Let me get it for you. So it looks similar with RSM. yeah. But the difference is that
Yeah, it looks similar.
yeah, the difference is that it only count for linear variables. So we don't it does not count for exponential, like the quadratic ones, the one we do raised to power of like square
Okay,
root.
square.
Yeah. And
Okay.
then it does not also count
Okay.
for effect of combination, like two variables combining. No, we usually have a b, a c, a d.
Something.
Yeah.
Maybe.
Yes.
Okay.
So
Okay.
it only accounts for the linear. So each of the variables, just like only them. So this is why the output equal to our intercept, then the coefficient of the first variable b1 s1. B is the coefficient of s1 first variable, b2 s2 the coefficient of the second variables, b3 s3 the coefficient of the third variables, till bnsn the coefficient of the last variable. So here we can have up to, we can decide to increase our variables. Even in RSM, you can increase the variables. So we can now decide to say, okay, let's increase the chemical descriptors to about 6 or 10 and see their direct effects on the biological activity. Then this one now, this last one here, stand for residual. We call it standard error. So we call this
Which
standard
one?
error. The E, yeah.
That epsilon.
Yeah,
Okay.
the epsilon, yeah.
Epsilon.
We call it standard error, okay. Is here, the error term. So we get that from the regression table. So quickly, what we need now, we have a table
The
of our training set with activity. So let us now go and get, we also have a table of the admet properties. So let us copy the properties we need from that
property.
admet, yes, the chemical descriptors we need from the admet file I sent. We'll copy it.
Oga Henry, sorry.
Yeah,
Oga Henry,
yeah.
please can you tell us the variables that are really like very important for
Good.
this?
I got that question. Now, what are the variables that actually has impacts on the biological activity of a structure? Any variable that plays role in the oral bioavailability has impacts on the biological activity, like
Variable that's
variables like molar mass, that is the molar weight, that is number one.
similar way.
The number of hydrogen bond acceptor, the number of hydrogen bond donor. Now the solubility, the TPSA.
That's TPSA, right?
Yeah, the TPSA is a topological surface area. Yeah, TPSA is topological surface area. So we account. So I will give you five. I will give you five.
Okay, what's the
Okay, let me open that the data. Okay. So one will consider the molar weight. So we can highlight the molar weight. We consider the molar weight. We consider the number of hydrogen bond acceptors. You can do with me. We'll consider the number of hydrogen bond donors. We can consider the TPSA, then the S log P for solubility. Now, these five variables, they are the major physiochemical properties, and they have direct impact on the activity of a drug. In fact, let me just tell you that drug likeness models are built based on these properties. Drug likeness models are built based on these properties. What I mean by drug likeness models, which I looked at them, they are models like as we are creating our own model now. So we are creating a model. They are models that have been built that helps you to predict if a compound can be like a drug. So they have already built the equation. So once you put in your structure, based on the properties of that structure, the model will tell you if that compound is drug-like, if it can be like drug. That is called drug likeness properties. And one of them is the Lipinski rule of 5. Now this Lipinski rule of 5 is a drug likeness model. And the condition is that your molar weight should not be more than 500 grams. We have discussed that before, that the molar weight should not be more than 500 grams. The number of hydrogen bond acceptors should not be more than 10. The number of hydrogen bond donors should not be more than 5. The solubility should not be more than 5. So Lipinski rule of 5 is built on these major properties. And that is why we are going to pick that same properties to build our model. This one is based on activity. At the end of this class, we shall also look at QSPR, which is based on property. But QSPR is not really medical. We can now apply it in physical chemistry, in material science, and environmental chemistry with other areas. That is where we really apply QSPR. But because it is based on property. But here is QSAR is based on activity, which is direct effect, biological effect. So having highlighted these 5, copy it. You copy it. I want you to work with me.
We are following you.
Alright, thank you. So I copy the 5. Go to that other file, the training data file. At your C, you paste. Now, there will be no need changing them to ABCD because we shall work with the label.
Okay.
So there will be no need to change them to ABCD. We shall work with the label for clarity purpose. So,
okay.
What we just need now is this is our training data. This is our variables that determines the activity. We have already explained that. So we shall now build. We shall now get the coefficients. So let's look for. This is the formula. So let's build the model that will give us this coefficients. So this equation is when we now want to predict, that is when we use this equation. If we now want to predict our new test data, if we now want to predict the activity of our new test data, we shall now use this equation. But first, we are going to build a model by getting these coefficients. This BO, B1, B2, B3, So we are expecting up to B5 because we have used the 5 chemical descriptors. So quickly,
Yes.
click on data. Click on data. So it's still the same process, the same place we use, but the difference is in the equation. So difference between RSM and ML is in the equation. So assuming we are using RSM, we would have created more.
I think Henry,
Yeah.
I thought you have done this.
No, we are freshing back for, because a lot of persons did not follow up. A lot of persons, so we have to share the
Okay.
data so that we can follow up properly, and then, hey, let everybody get it done.
Okay.
Yeah. So we now go to data and data analysis. So assuming we are doing RSM, we would have created more column with more variables. So that is what's the difference. The
Mm.
difference is the variables. So
So we just
yeah, click on regression. You look for regression. You click on regression. So this dashboard we open. So that dashboard we open. So on that note, what we'll do next is we have our input range, our Y range. Y is output, which is
why
activity. So you can select with the activity together because we include labels. So select with the activity. Then our input range, S range, the S, which are the chemical descriptors. You click here, and then you can now select also with the header. With the header, you can select with the header. So yeah, we are click on labels so that it will indicate those headers as the label. Then we are working with confidence level of 95. So click on confidence level of 95. Then you output range. Click on output range. So let's select where the result will fall under. You can just click anywhere below this table, anywhere below the data. So the result will appear below there. Uh, mm, there's no need for these residuals and others, so let's just leave that. Just leave that.
I thought you said the resistance is the epsilon.
No,
You make believe.
yeah, we'll still get it from the model table. Yeah, we can still get the standard error from the model table. So you just leave that part. So click on OK. So once you have clicked on OK, we can now get the model. So these are what we need now. So you can see because of the header we left, so it was able to understand our header. So these are those BO, B1, B2, B3, B4, B5. So these are the coefficients. So we are going to now use this to predict. So
Okay.
yeah, we can now use this to predict. And then these are their p-value, which is the probability at that 95%. Very important. This is For those of us that know how to interpret probability at less than 0.05, so you know what that means, if it is significant or not significant. So let me
It's not significant.
so let me see the intercept. Do you think is significant? The p-value is 0.561981.
Not.
Okay. I will assume that most of us has been using ANOVA. We know ANOVA already because in every research work, data analysis comes in after your laboratory work. So we are very, very familiar with ANOVA, which is the early tools that we have been using. Although we are moving out of ANOVA now, yeah, but people are still using that. So we can tell if it is significant or not. Okay, but that's by the way, that is for us. Now,
It's not significant now, but those values they are not significant.
yeah, yeah,
And they are not significant because they are greater than 0.5.
yeah. Now, here you can get the R square. The R square value is 0.6. The R square value is trying to tell you the correlation between the the uh, the input variables and the outputs, which is the activity. And we here I'm having 0.6. I don't know if that's what you have, but we should have the same value.
0.31.
Yeah,
In fact, your own values are even larger than my own. Mine is at okay. No worry. I've seen it. Don't worry. Continue.
okay. So
Continue.
uh, now 0.6 I think is okay, and the assuming is close to 1. It means perfection, which is overfitting, and if it's very poor, that means it's underfitting.
If it's
So
close to 1,
if
that means
it's
it's that's
overfitting,
your R squared.
yeah, if the house square is like 0.91, like 0.9, 0.8, it is very, very perfect. That is overfitting. Most times it means that the compounds are like almost the same compounds. Yeah, it means that the compounds are almost the same compounds. Now when you can try on your own, use one compound, use the same value, duplicate it up to like 10, but the same activity, the same chemical descriptors for one compound. You now duplicate it up to like 10. So by the time you do this, you see that you have R square value of 1. Reason because the chemical descriptors are the same, the activity is also the same. So it is overfitting. That means too accurate. But when there is a little variation in the structure due to similarities, then you don't expect to have that high accuracy. So that is also. Now what we now do is to build the formula.
Okay, so we are trying to
Now, but then building the formula, let us go and get uh, our
smart code.
yes, the test data now. So I wouldn't like to use one. Let's get like five different anthraquinone compounds.
Not only
Yes,
purpurine.
yes, not only purpurine. So let's get like five different, because
I cannot see your screen, oh.
that should be network.
I cannot see your screen.
Yeah, that
Log
should,
out and log back
that's
in.
network from your end.
Log out and log back in.
So
Okay.
so
So,
that's what.
Henry, which compound?
Let's let's look for. Let's still use purpurine. Okay, let me let me borrow those ones people did. I can't even. Can I find those ones people did before? Okay. See what we'll do. See what we'll do. Let's go online. Type
Which
purpurine.
one?
Don't bother. Type purpurine. Let's go to PubChem. We'll look for compounds similar to purpurine. Just they are similar compounds. So because they are all anthraquinones. Uh,
How do we get them?
um,